Thank you. Yeah, so first of all, thank you. Thanks to Jayanta for organizing this SETI session in this workshop, and particularly including an exoplanet talk, which is potentially linked with the search for life in the universe. So today's talk is, I am going to introduce a new frontier, which is essentially how to combine biosignature with technosignature effort to improve the knowledge of search for life in the universe. So I'm Liton Majumdar. I'm primarily based in Niger in Bhubaneswar, where I lead a group on exoplanets and planetary formation, where we ask the questions, how do planets form and evolve? What are exoplanets made of, and how we can observe atmospheres of exoplanet using various facilities such as James Webb, one of the primary example. So I came into the picture for SETI after this beautiful workshop that we have organized in December in Goa, where we brought together people from astrobiology, exoplanet science, and SETI, and to brainstorm about ideas how to make progress in the areas of search for life in the universe. As you can see from the picture, we have people from astronomy, radio astronomy, infrared astronomy, modelers from exoplanets, and also people coming from the geoscience backgrounds. So it was a fantastic workshop, and which helped to set up, some of the, collaborations, that I'm going to talk about today. So, exoplanets field is relatively new, and it was all started in early 1980s with the observation of first protoplanetary disk, and this disk are the places where potentially exoplanets are born. But the first discovery of exoplanets came around pulsar, which is around 1992. But the discovery of exoplanets around Sun-like star in 1995, which led to the Nobel Prize in 2019. Has created a renaissance for the field. Now exoplanet science is seen as one of the new frontier areas of astronomy and astrophysics, where people are contributing to understand how common are Earth-like planets around distant stars, whether we can detect Earth-like planets around Sun-like stars, how common are the Earth-like planets in the universe, whether we can detect any signatures for life around planets around other stars, what we can learn about how these planets are formed and how they are different as compared to what we see for Earth. So, and this is obvious because currently we have exoplanet populations where we have detected, more than 6,000 exoplanets as of today. And what I'm showing here, the orbital period with respect to the size of the planet. And as you can see here, large diversity of planets has already been seen, which are, as massive as Jupiter, and also planets like Earth. But there's a new frontier, which is basically the smaller planets, which is the frontier area now, where we have limited data. So the detection of Earth-like planets is still is the area that we are all trying, and this is the new frontier for the next decade. And this is exactly what was the recommendation from AstroDecadal. Because every decades, National Academy of Sciences from US recommends what are the top priority and what will be the next flagship missions that NASA should lead. So if you look at the recommendations from Astro 2020, then you will see there are two major recommendations. One is we should focus on, identify the area where we can identify habitable Earth-like planets by detecting the atmospheric signatures from them is one of the topmost priority area, along with how this type of planets were formed and how we can achieve this. The main two recommendations were we should build up, extremely large telescopes with, high resolution spectroscopy and high performance adaptive optics, so that we can, we can do direct imaging spectroscopy for, smaller, planets like Earth around distant stars. Along with, we should also build up, a space-based large observatory in the IR, UV, and optical, which will essentially do, direct imaging spectroscopy in the reflected light to, probe some of the atmospheric features which can potentially link to the habitability. And this mission is the next flagship mission after James Webb, which is, Habitable World Observatory. And this will essentially look for, signatures for, habitable planet around, sun-like stars. So having said that, the exoplanets fields are rapidly progressing, and the three main theme for exoplanet science is today, how to understand, if we study exoplanets today, it helps us to understand how they form, how they work, and also we can determine the atmospheric composition for distant planets to get the idea about whether we see some of the features which might be linked with the habitability for this type of planets. And this is why they are very important, because the atmospheres of this planet essentially encodes the information that we need to understand, life. So to tackle this problem, there are two ways to go about it. One is the biosignatures, and another is the technosignatures, because both of them are signatures from the atmospheres. And I will explain what are the key differences and what we can do about them. So the search for extraterrestrial life must proceed for exoplanet community by looking at the signature from the atmospheres. Either they will be biosignature or they will be signature related to technology, which is essentially potentially tracing the extraterrestrial life. And we define them as technosignatures. How we can do that? So when a planet passes in front of the host star, some fraction of the starlight passes through the atmospheres, and depending on the presence of different molecules in the atmosphere, light get absorbed at different wavelength, and these different absorption features gives you the idea about what type of molecules is present in the atmosphere, and that you can observe and constrain using transmission spectroscopy. And this transmission spectroscopy is one of the key techniques that we use to constrain atmospheric properties for different classes of planets today. And when you do that, then you get the idea about what is happening in the planet atmospheres. For example, here what I'm showing, typically if you look at Earth atmosphere also, what we see is, there is atmospheric chemistry happening in the planet atmosphere, and the atmosphere is continuously interacting with the surface, what we have on the surface. So in a typical atmosphere, you see escaping atmosphere, you see chemistry is happening in the atmosphere, and also atmosphere is continuously interacting with the surface. For example, if you have a liquid water and you are continuously releasing steam, and that goes into the atmosphere, and that interacts with the atmosphere, and it forms different type of molecules, and that we see today using different remote sensing measurement. So the atmospheres are complex. There is a lot of physics is happening, a lot of chemistry is happening, and that is also one of the reason why we see the effect of the climate and the climate change that we see today. So how we study these atmospheres? Generally, the atmospheres are constant using observations and simultaneously with models. And the modeling is generally done by considering this atmosphere in a simplistic way. Like you can consider the atmospheres in 1D, or you can consider the atmospheres in 3D, and you can predict what is there in the atmosphere. And you can use this model observable to constrain what is happening in this, in this type of atmosphere, and whether there are potential signatures that can link with the life in this type of planets. So I'm not going to talk about it, but we have been leading various efforts in this frontier areas on constraining atmospheres of planets around different stars, and how we can measure atmospheric composition. And when you measure atmospheric composition around different planets, how it helps us to understand how these planets form, evolve, and what is the future of this type of planets. So here, I'm just showing you some of the work that we have been doing in our group. We have this in-house model called Nexotrans, which is basically a modeling engine where you can use James Webb Space Telescope observations, and you can constrain what is what is there in the atmosphere, which has been trained using radiativity transfer, detailed atmospheric chemistry, and also the observables. And it is also run on machine learning framework as well. And when you have such model which can help you to understand what is there in the atmosphere. So this is the global atmospheric spectra coming from James Webb. So what I'm showing here, from 0.6 to 12 micron, the spectra coming from James Webb, from NIRIS observation, PRISM and MIRI data, and you can clearly see using transmission spectroscopy, you can observe key molecular features from the atmosphere. So such as sodium, potassium, water, CO, CO2, and SO2. So the key idea is, if you have planets and if you use transmission spectroscopy, you can measure atmospheric compositions by using transmission spectroscopy, and you can measure what is the amount for this type of species. And when you know this atmospheric composition, you can understand what is going on inside the planet. So this is the frontier area of the field. So now you have atmospheric gases, but there are also signatures which are potentially linked with the life. So let's talk about the biosignatures. For example, if you look at oxygen and O3, if you look at O2 molecular oxygen for planet Earth is largely related to the photosynthetic process, because if you have in the atmosphere, if you see a lot of oxygen in the atmosphere, that tells you there is ongoing photosynthesis process. And if you have ozone in the atmosphere, that means oxygen is photodissociated because of the incoming radiation, and you form O3. So if you have a planet and if you have an atmosphere where you see a lot of oxygen and O3, then you can suddenly think about this is a planet where ongoing going through a photosynthetic process. Then if you look at the methane, which is also one of the gas for planet atmosphere like Earth, where 90% is coming from the biological processes. So if you have methane in the atmosphere, then you can think is also possibly linked with the biological processes. Now, if you have planet where you have both oxygen and methane, and they destroy each other. So you need to have continuous supply of CH4 and O2 from the planet surface in order to build up detectable abundance of CH4 and O2 in an atmosphere. So if you detect CH4, O2, and O3, then there is a possibility you can think about this planet might be Earth-like, and there is and you can constrain some of the processes which potentially linked with the habitability. Along with that, if you look at the near-infrared features, for example, you can look at the vegetation rate age, so which is basically tells you there is a lot of vegetations, because all of this vegetation essentially has chlorophyll, and chlorophyll reflect lights in that domain. And this is exactly what we see. For example, if you take the infrared spectrum for Earth, we see a lot of ozone, we see CO2, and we see water. So water representative of, you have the liquid water on the surface, ozone is coming from the molecular oxygen, and you have CO2, which is telling you have atmosphere. But along with, if you have you can also simultaneously look at the features for these molecules, whether these features are broad, that will give you the idea about the surface features also, like whether the planet is susceptible to have water as a liquid form on its surface. Like for example, if you look at Venus, you see broad CO2 features, which is telling you have much more temperature than what you have for Earth. But for exoplanets, how will you go about it? So for exoplanets, what we do is we look for, we take the, if we really wanted to observe planet in the reflected light, where there is a potential signal for oxygen, O3, along with, other molecular features, you need to see planets in the near infrared UV and optical domain. And how you can do that? You have to image these planets using direct imaging techniques. So these Earth-like smaller planets, they largely orbit around distant stars in a wider orbit. So you need to block out the starlight that is coming from from the star, so that you can see what the planet, and you can constrain the planet composition using direct imaging spectroscopy. So here what I'm showing, a typical reflected light spectra for Earth-like planets from 0.2 to 2 micron, and you can see various features of water, oxygen, and ozone. So if you can detect these features, then you can have the idea whether the surface processes, which is because of the biological activity, can lead to the detectability of this type of features. And if you look at planet Earth from 0.2 to 2 micron, you can clearly see all of these features are present. For Earth, you see beautiful O2, O3, along with you see a Rayleigh scattering slope, and also vegetation, ray range, which is essentially telling you have a lot of vegetations and you have reflected light because of the chlorophylls. So when you are looking for an Earth-like planets around distant stars, we are looking for a planet atmosphere which can replicate, such atmospheric signal. And based on this, we have two instruments. We have two proposals from the community. One is Habitable World Observatory, as I was mentioned, which is for the next decade, where we would like to look for Earth-like planets around sun-like stars in the from 0.2 to 2 micron. And what you can see in this work that I have done with my student, what we can see various features like oxygen, O3, water, and CO2 can be simultaneously we can probe using reflected light using instruments such as HWO, and that can give us a lot of constants, and we can achieve high signal to noise ratio for these detections. Same thing. So there is also another mission which is coming up, which is also a mission concept, which is LIFE, led by European Space Agency. So here we'll be looking for Earth-like planets around Sun-like star, but not in the reflected light. Rather, it will be in the thermal emission. So you are observing the planet thermal emission directly. And for this, we'll be looking at the mid-infrared spectrum. So mid-infrared spectrum essentially goes from 4 to 18.5 micron, and you can clearly see. You could see methane and also the N2O. So this methane and N2O is another set of biosignatures that we can potentially probe using these facilities. So these two instruments, one is HWO and LIFE. This two instrument is tailored to do search for biosignatures in Earth-like planets around distant stars. And one in the near infrared to optical, and another in the mid infrared, and that will potentially help us to understand and characterize Earth-like planets around Sun-like stars. But biosignature is one way of thinking about habitability. But what about can we look for signatures which is related to technology? If you think about, if you have a planet where already life is already started and it's already civilized, and you want to look for signatures for technology, then what you can do? For here, just look at this figure. So here, what I'm showing the ozone concentration with respect to year. So we know with time, we all know about the ozone hole, right? This ozone hole is created for Earth because of the industrialization and release of a lot of chlorofluorocarbons. So when you release a lot of chlorofluorocarbons, then it goes to the atmosphere and it destroys ozone, which is basically one of the prime reason why we see ozone depletion in our atmosphere. And as you can see, after 1971, there is a drastic fall of ozone in our atmosphere, and then it again shoots up. So this drastic fall in the atmosphere is because this is the time a lot of industry came and a lot of chlorofluorocarbons was released, and we have destroyed so much ozone in the atmosphere. But then Montreal Protocol came into existence in early 1980s, and which is basically one of the environmental act which tells you how to protect ozone in our own atmosphere. So as soon as Montreal Protocol came, release of various chlorofluorocarbon from the industry, was controlled. And as soon as it was controlled, you can see, again, the concentration for ozone was increased. So these chlorofluorocarbons, which are potentially coming from, various industry and, can be thought as one of the potential, technosignatures for the atmosphere. And if we can detect this technosignature from the atmosphere of distant planets, then we can correlate them. We can correlate them with habitability as well. And so this is exactly the effort that we have been trying to do. So what I'm showing here, I'm showing a bunch of chlorofluorocarbons, so like CF6, C2F6, and some of the other molecules. Clearly, you can see all of these chlorofluorocarbons has signatures that is available from 2 to 18 micron. That's the region where potentially in the future life will operate. And when you have these features into the atmosphere, then if we record any atmospheric spectrum from the mid-infrared, then you can see whether is there any contributions, from any of these chlorofluorocarbon that help you to understand whether this type of planets are, this type of technosignatures are potentially present in this type of atmosphere. And this is exactly what Vishal was mentioned. So this work got funded by the Breakthrough Listen Initiative at NICER, and we have now excellent collaboration with Breakthrough Listen. So we'll be hiring a bunch of students will be working on understanding atmospheric technosignatures on exoplanets and possibility of detecting them in the future using instruments such as LIFE and HWO. And this is exactly important because there are so many missions are lined up for exoplanet science, and biosignatures is already a potential target for all of these missions, but technosignature is yet to be. So our responsibility is to also see the other part of the habitability, which is like how you can search for habitable planet using technosignature search. And we think, future, facilities such as Habitable World Observatory Life, and also as an Indian exoplanet community, we have been working on ExoWorld, would help us to, understand, the search for technosignature on distant planets. And with this, I will end here, and I'm happy to take any questions that audience might have.
Thank you, Liton. Questions for Liton?
Hey, hello, Liton. Vikram here. So, very interesting talk. I wanted to ask your opinion about the DMS and DMDS detection by Madhusudan et al. Paper.
Yeah, so thanks for asking the most difficult questions, but that's great. So the DMS on K218b, I think as a community, we think we need more data in order to see the features for the DMS. And one of the new finding from atmospheric chemistry community is DMS can be produced also by abiotic processes. So not only the biotic process, but you can also form it by abiotic processes. And that's why DMS is also been seen in the interstellar medium. So the two things which will help us to understand the search for DMS, one is we need more data to potentially locate multiple bands of DMS. And by the way, for the DMS, the lines that has been used to, the opacity which has been used to detect this molecule is not really high sensitive data. So there is also needs for improvement on the data set, that part. Together with, we need more data so that we can see multiple other bands of DMS using James Webb. And then when you see that, then we need to have models which we should see how much is the relative contributions of DMS coming from abiotic versus biotic, because clearly there are abiotic processes active to form DMS, and whether those abiotic pathways are active, that one needs to see. And so this is a challenging problem, but community is up for it. Yeah.
Take one online question. Ramesh?
Yep. Can you hear me?
Yep.
Thanks, Liton. That's a very interesting presentation. Even though I don't work on this field, I'm primarily a pulsar person. I find that very interesting. Maybe my question is sort of peripherally relevant, I should say, because I was at a pulsar conference recently where some interesting results on first molecular carbon detection in one of the exoplanets, planets around pulsar, I should say. I know about that pulsar because it is one of the Parkes discovery. Just to put in the context, it is like 200 parsec kind of a distance and 1,000th of a solar mass kind of a companion. So that's what we are talking about. So JWST observations had a clear detection of C2 and probably C3 as well. So my question is, obviously, it is probably not a potential candidate for technosignature, I understand. But my question is that most of your targets in the exoplanets category will be much closer. So could you comment on or tell me a little bit about similar sort of attempts have been made on prospective targets? What is the state of the play?
Yeah. So that's a very nice question, and I did talk about it. Let me see. Yeah. So yes. So currently, if you can see here, so the large part of the sample that we have been characterizing using James Webb, the most of these planets are very close to their host stars because they have, some small transiting period because they are observed using transit photometry. So we are probing planets which are hot and very close to their host stars. So now if we if we define life based on what we know on Earth, then Earth-like planets, based on the planet formation theory, and if you want to have water as a liquid form for the primary criteria for habitable planet, then it should orbit a distant stars a bit farther away. So as soon as your planet is orbiting farther away, its your transiting period become much longer, and it's not a suitable target for you to do transit spectroscopy. But which is the main target, which is the main tool for our atmospheric characterization. So for this type of Earth-like planets, you need to do direct imaging. So you need to image these planets by blocking the starlight using a coronagraph, and that's exactly the next flagship mission, Habitable World Observatory, where the Earth-like planets around distant star will be observed using direct imaging, and simultaneously we'll be doing reflected light spectroscopy, which is the light reflected from the planet, the starlight reflected from the planet to the observer. So that will give you the idea of the atmosphere. So we are not yet there to characterize Earth-like planets using James Webb, but now there is effort. I must say that but you can always look for Earth-like small rocky planets around M dwarfs, because M dwarfs are much cooler, and you can have rocky terrestrial planets orbiting much close to a star with a smaller transiting period, but still you can have a habitability. So this is a new search that's just been initiated, which is basically a legacy survey of characterization of Earth-like planets around M dwarf stars, and to learn. But the results are just beginning to come. So I would say Earth-like planets is extremely difficult around Sun-like stars, but around M dwarfs we'll see what is waiting for us for the next few years, but we are not yet there to characterize this, Earth-like planets in detail using transmission spectroscopy. Yeah.
Thanks very much.
Yeah.
Thank you. Any other questions? Yeah, there's one.
Thank you for the talk. So could you go to the last slide where you showed the spectra for CFC molecules? Yes. Yeah. So is this a simulated spectra, or did you observe in any of the exoplanets?
So these are the simulated spectra. This is not my work. So this is from H. Schwarman. So this is a simulated spectrum by considering different concentration of CFC. So what you can see here, so the you have a black line is Earth-like planet atmosphere, okay, and this is the thermal emission spectrum from Earth-like planet, the black line, without considering any technosignature gas. Now, if you assume, but clearly when you have that, you can clearly see there is a ozone features, there is a water features, and there is also CO2 features. So now you are assuming if that particular planet is, is a good target for your technosignature search, and you are assuming you have 1 ppm, 10 ppm, 100 ppm of chlorofluorocarbons. How does your spectra changes, right? So each of these different color representative of your Earth-like planet with technosignature gases with different concentration. But we don't know any of this, whether what will be the concentration for these chlorofluorocarbons, right? So this is just a model prediction. So if you have Earth-like planets, a template spectrum, and now if you assume different concentration of technosignature gases, then you clearly see differences. Now the question is whether these differences are sufficient enough to be resolved by future observatories. So that was the main target for this paper that H. Schwarman has shown. So these are all simulated spectra.
Thank you.
So I have one question.
Yeah, please.
Anyone produce a spectrum of Earth from faraway satellite on similar wavelengths, and how do they come back?
Oh, so
how Earth looks from the farthest spacecraft, the spectrum of Earth?
So basically, are you asking? Let me understand. So are you asking how Earth-like planet around others?
Not Earth-like, Earth spectrum of Earth.
How it differs as compared to our Earth, right?
These lines look from a faraway spacecraft.
Oh, okay. So you are asking if we observe Earth from other spacecraft, right? Yeah. Okay. So there is an effort on that. So basically, observing Earth as an exoplanet, right? So even if you look at Chandrayaan has a payload where Chandrayaan-3 has a payload which is basically SAFE instrument that wanted to look Earth using polarimetry. So you from moon surface, you were trying to observe Earth signal using polarimetry, right? So there are efforts. People are trying to observe transmission spectrum for Earth using a distance spacecraft, of course, and the constraints that we have currently, for example, the constant that we have. Like we have, if I'm not wrong, we have some measurements from epoxy. Epoxy has some of the measurements, and it gives you the good constant on what you have in the atmosphere if you measure with the low cut radiation sensing measurement. So we have some measurements, but not much. But this is also another topic that people are started, integrating in the community, observing Earth as an exoplanet from using other instruments.
Thank you. It's interesting. Any other questions before we have to break for lunch? And if not, let's thank our remote speaker, and you can always get in touch with him.
Thank you.
Thank you. Thank you. Thanks again.